that I might blow up this microphone. I'm not sure. But behind me is a web address on Dropbox, my Dropbox account, the public folder, and you can download the compressed file that comprise the notes and the resources to this talk. The intention is that, and I'm going to probably pay some sort of homage to what I was experienced last year in Pi, Ohio. And that was the fact that I tried to incorporate actually being able to edit code, the attendees to be able to edit code, and to be able to experience Python editing and putting a Python program together. But that was too aggressive, too far-reaching. I never finished my talk because we were all, besides it was 100 degrees in this room at that time, for those of you that were here last year. This year I'm going to, with your permission, I'm just going to give a straight presentation tutorial. There's no going to be, we're not going to write anything, but I do want to provide the materials for you that after this talk you can go and actually, as I call, reverse engineer code. Actually, another word for it is to pirate. But to reverse engineer the code and to understand the various components of a game engine. So let me get started. Speaking of time, let me get started with the talk so that we can be sure to get everything in. For those of you after the talk, for those of you that want to get a copy of this, of the same compress or the same folder, I have flash drives if you want to download them. And you can do that as well from my flash drives. Okay, let me go back to the beginning. Here's my postmortem. This was after last year's 2011. Basically, what I just said, that this year I'm just going to give a straight presentation, certainly ask questions whenever you want. But I'm not going to try and involve everyone in editing code and everything like that. So we're just going to look at the various components of a game engine. The website here, www.panda3d.org, is are the people who maintain the code. It's actually maintained, here's my page and my email address at Columbus State Community College. I'm a faculty member there, and I coordinate the game programming track at Columbus State. Panda3D, again, distributed and maintained by Carnegie Mellon, developed by Disney, was initially the inspiration to develop the Panda was Toontown, Disney's massively multiplayer game that must be, I don't know, 10 years old or something like that now. I forget when it first came out. But basically, when you use Panda3D, you have to open up a command console, and you've got to do all the DOS things of changing to a drive if it's on some other drive like F or E, if it's on a flash drive or it's on some sort of external disk. And you use the command ppython-intro.py. And for that, and I'll show you that in just a second. First of all, we're going to the camera control. For when you get into Panda and you see it displayed in the game window, the right mouse controls the zooming in and out. You hold the mouse down and you slide it, I believe, up and down, and it will move you in and out. The left mouse button is for panning, left and right, and the middle mouse button is for rotating the scene. Panda is a 3D game engine, so you are working in 3D. Ultimately, to create this multiplayer game, I'm going to talk about it in 4 stages. Stage 1 is adding objects to the game. Stage 2 is actually taking the object that is your player and giving him the ability to move around in the scene through the keyboard controls. Stage 3 is we're going to be dealing with collisions. Wouldn't be much fun in the game if you couldn't collide with something or someone. And stage 4 is the wiring. We're going to wire our network, and we're going to discuss some of the issues. Now that's going to be the long session because there is a lot to networking games, and I'm going to gloss over many parts of it and leave it for you to discover, but I'm going to hit the salient points of the networking and the features that we're going to use in the game engine itself. We are going to use Python's object-oriented programming style. For those of you that are new to Python, please bear with me. I'm not going to be talking in extreme Python, Python linguistics or syntax or whatever. I'm going to try and make it as general as possible, but you should familiarize yourself with, when you get into something like this, you should familiarize yourself with the object-oriented style of programming in Python. That is how the games are instantiated, because the game itself is an instance of a class of games that is defined in Panda. In the object-oriented style, we're going to talk about how the class object is created. The class name is PyOhio, and we create when you see this funny little def that is in the code itself, it says def _ init and so forth. That is what's called a constructor. In object-oriented talk, a constructor is always called when a object is instantiated as a class, and it basically initiates the object itself. It creates all the details in the object. And here are some of the features. Pay attention to indents. That's why you should, whenever writing Python, you should always use one of the accepted editors. I'm old-fashioned and I use idle. And I've gotten so accustomed to that. I've tried others, and they're good to use. Others that look a lot like Visual Studio, but they're Python. And but I just go back to idle all the time because it's kind of like riding on a tricycle. It's easy to, you don't lose your balance on a tricycle. The def is, with the green arrow pointed to the def, that's indented once. And then everything that is included in that constructor init is indented twice. Python, as if you've attended the Python Beginning Sessions 101, you know that indents are the scoping mechanism for Python. So everything that's indented twice would fall under the scope of the constructor init. And we'll be looking at that a little more when we start building our game. There's the Dropbox account for any of those of you who, I will put it back up at the end of the session, and if you haven't copied it down yet, if you want to. And let me escape from there. So, I'm going to. Now, what you do is down at the bottom, I don't know if you can see it, but down at the bottom, I'm going to open up I have pinned to the taskbar a command console prompt. I'm going to open up this window, and I don't know, can you see should I make the letters a little larger? Are they all right back there in the back of the room? Okay. Here we are in DOS, basically. It's the operating system that runs on the Microsoft Windows, and everyone has a, whether it be Mac or Linux, you always have a window that is command-driven. And so, let's see, I'm going to go to my Dropbox. I have a folder. CD means change directory or change folder. Not Dropbox, let's see, desktop. Sometimes you hit the tab key, it auto expands. And I'm going to go, the backslash means I'm going to this folder, desktop, and I'm going to go to a folder underneath called PyOhio tutorial. I don't think that's, there's the one I want to use, yeah, PyOhio tutorial 2012. And you can use the tab key again to kind of leaf through all the folders or all the names under a particular folder. And you can use the dir key to look at the contents of that folder, all the other files. Now here is intro.py, all the Python files that I use, and everyone who writes Python code extends their code with .py. To run that intro.py, you type the keyword that is tied to Panda, python. That stands for Panda Python. And then you, of course, your intro.py. And when I do that, this was working. Let's see, open stage 1. Oh, I know. I must have copied that. Okay. Let me show you what Python code looks like. We'll go right to stage 1 here in just a minute. And let's go into, if you want to, sometimes you can automatically bring up, right-click on your Py file, and it'll have like, here's another editor I use, the Wing IDE 4. It has a cost associated with it. And I am also a big supporter of open source software, so I tend to only use license code when there's an absolute need for it. This is what Python code looks like. And I'm going to ask you to forgive me. We got a lot, this skeleton code has a lot of information. The top part here imports a lot of libraries that we're going to use. They're standard libraries when developing a Panda game. You see down here, I've set up some global variables that I use, like the value of pi is calculated, which is dumb because Panda in its math library, you can just use math.py, and you've already got a value of pi to like about, I don't know, 25 places or something like that. So I'm an old-fashioned programmer. I've had these global variables in my code forever, and I always seem to put them in, even though there are a lot easier ways to do it. These global variables, they're constants, and I'll explain those later when we get to networking, as well as that. Properties, window properties are something where you can hide the cursor. You can make your game full screen automatically when it's opened. So those are some features that you might want to explore when you look at the Panda manual. And let's see, so here are two functions for adding instructions to the screen. The Panda code on-screen text is a command that puts a message in a particular position with a particular format, and you can't quite see the. And one thing about idle is you can't scroll horizontally, so you can't see the end of the code. But when you download the code, you can certainly experiment with that, and you'll see the example of it on here in just a minute. So let's go, and this is just to, again, notice that over here I have my cursor. That idle knows that it's going to indent. Now the big thing about Panda is that you need to tabbing in means 4 blank spaces. And if you were using Notepad or Word or some other kind of editor, Emacs, you'd have to remember that every time you wanted, you'd have to either set up your tab keys to do 4 blank spaces, or you'd have to remember to hit the space bar 4 times, which is really incredibly time-consuming and tiresome. So it's nice to use a Panda editor to be able to keep track of that. And all you have to do is know how you push 1 tab or 2 tabs depending on the scope of the code that you're writing. So once we get inside the constructor here, notice that these commands are now double indented because they fall under the control of the constructor. So when a game is instanced, it immediately calls this init function, and then it starts to build the game and the details. And some of this I'm going to leave until we get to networking, but I put them in there. Here is some, I'm setting the instructions on the screen, calling those functions above with the text that you see there. Basically, to let the user have some idea of where of what to do in the game. And the floating point values that you see with the add instructions are merely a placement horizontally, or I'm sorry, vertically, up or down. Okay, so 95% of the window or 90% of the window. And to do that, sometimes you just experiment. Set the background color to black. And let's see, where did I think that, let me get out of this. So that's just a flavor of what the game code is going to look like, and you're going to see a lot of this. So let me get out of this, and let's go into stage 1. Let's get started. Now first, before we get started, let's take a look at, this should run here, so stage 1, add objects, dir. Okay, trying to raise this up a little bit. I'm going to run the Python code to give you a little introduction. Now the stage 1-start py is a skeleton code, and basically brings up this window. You're in the game now. We don't have much in the game. And we have our instructions over in the upper left. We have our title down in the centered in the bottom. And we're ready to start filling in the template for the game. Okay. Now I've already keyed in, when we look at keyboard controls, I've already keyed in the quit function using the escape key. And we'll look at that here in just a second. So let me... Adding objects. So the first step you want to do is you want to take your creations and you might create your geometries that you want to bring into the game through Maya, or Wings 3D is my favorite. It's a free modeling software. that has a lot of nice features. Blender is another, it's an animation tool as well as a modeler. And when you create your geometries, there's certain ways in which you can, a particular way in which you can convert to Panda format, and that's called the egg format. So here you see a typical command where you output your geometry in DirectX format, and then you use the utility code x to egg to convert your sphere, or my sphere, to an egg that I can directly import into Panda. And all those objects you can look at, they're in the folder under here called Assets. You can look at there and you can see them listed. Now the constructor again basically contains all the instructions for how we want to bring in the objects. And it uses the method, the instruction called loader load model, and you place a string in the argument or the parameter for that function, and you assign it to a name in the game. Now, one of the object-oriented features that I'm going to be talking about is that variable on the left-hand side of the equals, and the self is always present in an object-oriented code. It means this variable is associated with this instance of the game and no other instance. In other words, the PyOhio instance that is the game is going to be able to reference that name, and no other class instance can reference the name in PyOhio. We might create another PyOhio instance, but I've never done that because you would have conflicting games running at the same time. But we can always talk about more advanced techniques for developing games. And then the function loader load model is a particular command that says go into the assets folder and look for something called sphere.egg. And of course the shorthand notation means you can leave off the .egg, it'll always look for that. Okay, so as you see here at where I have self.fighter, loader load model, and then the assets folder, and then the sphere. We use the method underneath that, reparent to render. Yes?
Is that load model, is that purely graphic in nature, or is that actual code base, the asset sphere?
Actually, I'll show it to you in a second. Yeah, I'll show you where it's located. It is an actual geometry file that you load in. Right. I don't know if I answered your question, but yeah.
Geometry, so it's purely a graphics format. There's not really like code methods attachment that you're loading with that.
Oh, yeah, I see what you're getting at. Yes, that's true. This has like, if you were to put the egg file in an editor like Notepad or even, Notepad++ is one of my favorites, you would see the points and polygons defined in a particular format. And of course, every geometry format has its own look. You know, like the Vermal format has a very HTML-like look to it. The Wavefront OBJ has its own definition. So it's yet another format, or not yet another standard, as I should say, because everyone has their own format for developing the geometries. The reparent to render. Everything in Panda is developed on this scene graph idea. Render is the root node because everything you put under render is what is created in the scene when you see it. You can create other nodes that aren't reparented to render, but it's only when you reparent to render or you reparent to a node that's under render that you get these, you get them created in the scene, actually rendered in the scene. The scene graph has some important concepts, but I think the the most important is that if you don't reparent to render, it's not going to be in your scene. And the other, as you look, you see the other methods, also called functions, like set position. Basically, when you call self.fighter.setPosition, you are actually calling the method that is defined for a model, and it sets it at a position in X, Y, Z. Yes?
What did fighter inherit from? What did fighter inherit from? Fighter inherited from another class, correct?
From the model class. When you said load, when you say self.fighter equals load model, it becomes has all the characteristics of a class of model.
So loader is like a class loader.
Yes, that's right. That's right. And so fighter now is an instance of that class, and it has all the methods under that class associated with it. Like set position. Set HPR takes 3 floating point values, and HPR stands for heading, which is I always forget the plane analogies, but there is, I know this is yaw, or no, that's pitch, yeah, pitch. And roll and heading, right? That's yaw, okay, thank you. So basically HPR stands for the 3 angle directions that would control those. So if you have a negative roll, you would be rolling to the left. If you had a positive floating point number, that would be a degree of roll to the right. Same is true for pitch down, pitch up, and heading. Negative values turn to the left, rotate to the left. Positive values rotate to the right. And they are in degrees. They've gone ahead and they've associated those with degrees. The set scale, of course, is 1 floating point value. You just set you can scale up the size of your model. These are typical controls for any computer graphics like scene. And the color scale is one in which it's a multiplicative. It's a 0 to 1, and you take and you multiply the color that is in the object by the value associated with red, green, blue in those positions. So to say set color scale 1.000 means to give it maximum red, but take away all the green and blue. So you got a red object. Now this doesn't do any good with a black object, because what that 1.0 does is it multiplies the black-red channel in the object by 1. So 1 times 0 is still 0. So many times you would want to create your object such that it's white, so you have the maximum ability to kind of twist those colors around. And we'll see that in a second as well. I'm going to create, the design of the game is going to be simply to put a barrier of, like a reef, and the objects are going to be positioned on a circle, and we are going to leave a little gap in the circle so that our hero can get in and out. Okay. Now, obviously, who you're playing against are the enemies. So they're the enemies, you're the hero. And of course, on the other machine, they're the hero and you're the enemy. But to produce that barrier, we have to use a little trig. And so we just use the unit circle and a little bit sine cosine. And I'll show you. So that formula is too small for you to see on the screen there, but I'll show you that in the code itself. And of course, the argument to cosine and sine is in radians, not degrees. And radians, of course, is that measure along the unit circle that goes from the x-axis up, and you go up, I think 1.0 is about at 57 degrees approximately. Okay. So here, let's see, there's the formula. And I'm only going to put it in 2D. Of course, it's cutting off the right-hand side of that formula, so we'll bring that code into focus in idle in a minute. But let's see. So here's our loop. The for loop, for I in range 100, we're going to produce 100 of these. The range function in Python creates a number 0 to 99, always n minus 1 of the argument that you place there. We attach a new node. That top command says we are going to put this new node under render. It's not going to be floating around in our scene graph. We are going to attach it to render so we can render this thing. We set the position to that of the trig functions, cosine and sine, so that we can calculate an x and y position on that circle. Okay, and they will occur in a circular configuration. And then the next three calculate a random number for color. Random in green, red, and blue. And I use those values to set the color scale. Oh, that 1.0 at the end, that's an alpha channel. For those of you that aren't familiar with computer graphics, alpha channel means transparency. 1.0 is fully opaque. 0 would be fully transparent. So later on in my course, we get to stealth and start coloring objects with like environment maps and transparency so that you can sneak up on people. And now the important part is we call up above, outside the for loop, I set up an object called self.parent. And again, it's a model. It uses the sphere geometry. And we set the position that we don't really need to set the position because we're not going to attach it to render. We're not going to render it. But we are going to use it in the for loop. So we can take that geometry and we can place it, or we can call that geometry and create that geometry for our placeholder, our little object inside the for loop. What this does is it's a tremendous savings because instead of having that geometry repeated 100 times, you only call one instance of the geometry. And they all share the same geometry while changing things like the color and position and things like that. Okay? And that's what it looks like. So here's in the center, that little red, is that too small or can you actually see it? There is our little red hero in there. That was our fighter, self.fighter. And our placeholders, there are 100 of them that form a barrier. Now, this is the design of the game. And I call it a game because no sooner did my students in the class did we play with this concept to get a start on Panda, in that when we got it networked, they immediately started like picking on one person and blocking them in or out of the circle. So you can take some very simple concepts and develop games, especially when you involve other people. Now that small opening I referred to, again, is since I have the small opening, there are 100, and basically if you look at 100 divided into 2 pi is approximately 0.06. I like to use approximation when I'm doing math. I don't like to go into great detail, but that 99 times 0.06 comes up to 0.94. And 2 pi is 3.14159, and so on. And that explains that little small gap there. The difference between 594 and 6141 is that small gap. So that you don't, if you were to do, let's say, a number of iterations so that it did come up, instead of doing 99, let's say you did like 10 more, you would see the objects start to overlap the first ones because it would come around and it would reproduce the same positions on the, as it went in a full circle, 2 pi. Okay. Now, I'm going to use, this is the kind of the method I'll be using today, is that I'll give some overlook or overview, and then what I'd like to do is go in, show the code, and then run it so that we can see, let's see, where am I? Let me open this up with idle. And here are the commands down here. Again, we get past stage 1. I've put these comments sprinkled throughout the code, so that it's hopefully easier to read. Here's a little command a sequence of commands that you can use to disable the mouse control of the camera, and that'll come later on. We'll look at that a little later. But here's an important feature we're going to be using over and over again. This command, self.accept, is a method that's defined under the game properties. And it means you're going to accept a keyboard input, the escape key, and we're going to tie it to a function called self.quit. Okay. Now the function down here, starting with def, means define a function, call it quit, and we're going to pass this self. This is self is a constant call, that parameter that's passed in functions. And simply, you'll notice that the indentation for that def quit is popped out 1. We're no longer under the constructor. These functions are defined outside the constructor, but inside the game. So 1 indent. Then 2 indents for the command sys.exit. Okay, and that simply just quits the game. That's all we're doing. I wanted to put that escape quit function in there because a lot of times when I'm doing talks, all of a sudden I forget that I don't put it in and I can't quit out of the game and I have to go through all sorts of monkey business. So, just to complete the discussion about Python, down at the bottom you see in the main part of the Python code, you see s equals pi Ohio. That means we're making s an instance of the class pi Ohio. And to run the game, we simply say run after that. And then the game takes over with the game clock and everything else. Okay. So let's see. Now, I'm not used to my mouse being up here on this high. Let's go back here. Now I have CD++. Wait a minute. Okay, it's back again. CD++ means just go back up to the parent folder. And in the distribution of the code, in the folder called Final Code, are the finished products of each stage. My process was I would put the skeleton code under each stage. We would work on it, produce a final result, and see if it runs. But the final code under that final code folder is where you will find those things, those Python scripts that so far, hopefully, that will run, unless I screwed up on that first one. But so python stage1.done or -done.py produces this. Okay. And again, I'm going to make the screen full. I could have done that in the configuration in properties, but let's just go through the process. Here's a full screen. Mouse button, right click, zoom in and out. Middle mouse button rotates. Okay, so here we have a game that is in 3D, but when I get to the client, I'm going to fix the camera. So all the client can do is just look down on it. And we'll discuss the relative merits of that, but this is our game. Here's our hero, the red guy in the middle, and our barrier that's outside. Now we can't do much. I mean, there's nothing binding that character. So that brings us to the next subject. How do we make a move? And that's in stage 2. Okay. Escape. All right. Now, if you don't mind, I'm just going to blast through for the first hour, try and get through stage 2, and so that we can get everything in. Last year, I had a difficult time getting the whole. I only got through half of the presentation, so I'm determined this time. Okay, so let's go on to stage 2. Driving the player. If you go into the skeleton code and even the finish code, the done code, you'll see that stage 2 banner in command and comments listed. Now we're going to. The game uses an event-driven cycle. In other words, it keeps rendering the scene, and when it detects an event being given by the user, it immediately acts to that event. It reacts to that event, how it's programmed to react. Now, our input devices are keyboard and mouse. And we could easily, in Panda, you could easily configure a joystick or some other device to control everything. And each key has a tag name. Okay. And you'll notice here, I left my light pen at home. Again, our self.accept. Remember the escape key? Well, in Panda, that escape key is known as, quote, a character string called escape. Very much like the arrow keys in the lower part of your keyboard, lower right, are known as arrow underscore left, arrow underscore left up. Okay, the event when you push a key down, like the left arrow key, that produces an event called arrow left. When you release it, that produces an event called arrow left up. We're going to capture the creation of those events here in a minute. Okay. Now the self.accept says we want to bind that event, the arrow left key, to a particular function, to a function that controls that event. The one, that is the argument, I should say, the middle argument, self.negx, is the function name that we're going to create in outside of our constructor in a minute. And the 1 in the brackets means send a 1 to the function when this happens. And then we bind we call the same function when we release the key, but this time we send a 0. So this is our way of monitoring what is happening with that particular key. I think this is, so we're going to see how this function, negative x, allows for continuous movement. In other words, you hold the key down and the player always moves to the left. When the key is released, it sends the value 0, and we're going to remove the task from the game. Now, I haven't introduced, I see here we got the code down there. Now, here's neg x. Def neg x. Notice there's only one tab in for the def neg x, and there are two tabs in for the if and else. Now, when it says if key down, that means check the value of key down. Anything but 0 is always true. Okay? So if this function is getting a 1, it's always true. And basically, what happens in Panda, there's something called a task manager. And the task manager's responsibility is that every clock cycle in between the renderings, it does all the manipulation, all the calculations that are required to drive the game. And so what happens is we add the function self move neg x, and we give it a tag. That character string is merely a tag for that particular event or that task. If it's 0, that means we've lifted it up. If the task manager removes that task that was labeled move neg x, and we just clean out the buffer by saying except once. Except once means do this one time and then finish. And that cleans out the task manager's responsibility for this neg x. There's the move neg x. And the parameters in the call, I won't go into detail, but basically self is always the first argument in a object-oriented function call. And task merely passes the task manager information to this function. And here the self.fighter, we set the x to -1. We set the object's position and we subtract 1 from the fighter. That means what its current position is, and then we just subtract 1 from it and move it to the left. Because x-axis goes in that orientation. Negative values go to the left, positive to the right. And then the very important comment on the end there that is a part of neg x is the return. Because this drives it so that as long as we hold that button down, that return task continue says keep this task in the task manager until told otherwise. And here's like a complete listing of our accept functions. Now, I should also mention that our self.accept declarations, commands, are all in the constructor. And these operate on the 4 directions. We're going to play a 2D game. It's going to be in X and Y, and we're just going to operate in the XY plane, and we're going to go negative X, negative Y, positive Y. Okay. As I said before, the accept once method, when you release the key, it sends a 0 to neg Y. It's that if condition is evaluated as false, it tells the task manager to remove the task, and accept once basically clears that buffer, clears the instruction out of the task manager. And here this is where if you were to go into stage 2, the Python code is there, it's incomplete. You would want to see if you could write the code for the other 3 directions. But what I'm going to do is, let's go into Yeah.
So your accept calls a callback, which calls another function which modifies the task manager, sets the job within the task manager.
Yes.
Why doesn't the callback that accept is calling just directly modify the coordinates?
Well, in the Panda game is if you were always calling that function as you're holding the key down, it would freeze the console. It would freeze the game engine. That one function is always is holding on to the instructions from the console. What we're trying to do is we're trying to, I should have pointed it out, but when we set up where negx calls move negx, we're trying to free up the game engine so that you can push 2 keys down if you want to. And so when the task manager takes control, let's say you want to move positive y and negative x. Okay? So it frees up. It's a non-blocking read.
Okay, so the task manager handles doing the re-rendering outside of your typical event.
That's right, outside of the event-driven cycle. Oh, sure. That's a good point. I'm sorry I didn't mention it. So let's do let's see, I think I can stage 2 done. And here's a full screen. Let's move it out. Again, when we get to the server and client stuff. Okay, so here we are. Here's our hero in the middle. Move left, move right, up, down, and we have, and also if I push 2 keys down, it can move diagonally. Like that. But we're missing that so very important component in a game, and that is we can't collide with anything. Nothing stops us. Okay? So, I'm going to say, let's take a 5-minute break, real quick break. I don't want to take too long because the next section are a little more complicated and I'd like to get through them. Okay? So I'll start in exactly 5 minutes at 2:56. Is collisions. We want to be able to collide with things. Ultimately, we'd like to be able to collide with things and make them blow up, but that's another topic for another year. But so we need to be able to tell the game when 2 objects are touching one another, when they're actually colliding with one another. So Panda has a number of collision algorithms. We're going to use the simplest one. We're going to use the pusher collider. Okay? There are other colliders that say that when 2 objects hit, it calls a special user-defined function which handles the collision in a certain way, like explosions and things like that. But we're just going to use the collider functions that basically impede the objects from going through one another. As I said before, the pusher collider is the simplest. And what the pusher collider does, it has an internal function. 2 objects collide, it simply pushes them back. Now, to be able to trace this through our game architecture, we need to assign to each object a collision geometry. And to each of those collision geometries, we need to associate a collision node that is under that model. And of course, the simplest geometry to detect for collisions is the sphere. If you have 2 spheres with different radii, on different objects, and you test the distance between those objects, then if you test the distance, once that distance gets to what value do you think you'll detect a collision? The sum of the radii. Okay? So that's very simple. You know, other types of collision geometries are quite complex in their nature, but certainly the sphere is the simplest and one of the nicest to use. So here we go. We create to the fighter, that top command, we want to attach collision geometries to both the fighter and the parent. Because remember, the parent generates the placeholder. The parent is the one that generates the actual conditions for the instanced objects in the circle. So to self.fighter, we call a method that belongs to the model class, attach new node. And so if you look at this as a tree structure, you got render up here, you've got fighter as a node attached to render, and as a node attached to fighter, you have this new node, and it's of a collision node, and we call it C node. I called it C node too. You can give it any tag name. To the parent, we do the same thing. We have these collision nodes now that are attached to the parent and the fighter. And to that node, the bottom two commands, we create geometries that are attached, that are added to those collision nodes. And that command says 0, 0, 0, meaning x, y, z, and that placement is relative to the geometry. So that 0, 0, 0 should be the center of the object, the center of our sphere in this case. And we give it a radius. The fighter, because of its size, we give a radius of 1. To the parent, we give it a radius of 2. So it's a larger collision sphere. Will detect a collision a lot sooner than you might expect. But you can play with these values. Let's see what okay. Yes?
There's something funny about your microphone.
The objects that are labeled with the here we have the assignment of the collision handler, the pusher. We create a variable under our game class that is, the variable is named pusher, and it's of a collision handler pusher type. Okay, that's all that function does. And we add the collider, we add the fighter collision node and the fighter to the pusher collider. Now what that means is that the fighter is going to be the object that's tested into every other object in the scene. Okay, so what happens is the fighter is called the into object. Okay. I'm sorry, the into objects are every other object in the game. The fighter is the from object. We haven't seen that term yet. So what happens is that every time we go through the scene, the fighter is tested to see if it's colliding with anything in the scene, and it goes through the render graph. It starts with the render, it goes through every object that is not the fighter, and checks whether or not the fighter's collision sphere is intersecting with something else. And then what happens is that if the simple collision occurs, it starts pushing back the two objects. Actually, it pushes back the from object. And here we have, again, this is just the game code. We have to set up a traverser. And we the from objects included in the list of, are included in the list of objects to check. The show collisions, or I should say the traverser is of type collision traverser, which means it's going to start with the render and go through the entire tree of the scene graph to check for these collisions. And then we set up a collision handler that is basically associated with the base game class and is called, you can put any name, CTrav is just one I used just to set up that traverser as the base traverser. And that next command, the traverse, sorry for these terms, but the traverse method under traverser says start with the render. Okay? In other words, travel the whole graph. We could have started our traversing in another part of the scene graph lower down, in another group of geometries if we wanted to. But for our purposes, we're going to start with the top node and we're going to look for everything under that render node. And that the last command on that page, show collisions, basically just is going to show when we do collide with something. What it does is it highlights the spheres that are the collision spheres, and it even puts a little red dot where the collision point is between the two spheres.
I don't understand the base CTrav.
Yes.
So you said CTrav can be any variable. So what are we attaching to base block?
Basically, the base CTrav is the method that, that is known inside the base game class, the parent game class.
Okay, so CTrav is a special thing to handle.
Yes. Yes. Yes, you're right. The CTrav is a special asset under the base class. You're right. Now, here's a page that's supposed to show all that code together. You can't see the details, but we'll take a look at that in a minute. But it basically is a review of every command that we've done and focused on. So let's take a look at let's see. And stage 3 done should look like this. I'll make it full screen. And so now when we start moving our mouse, or start moving our hero here, let me get at this a little closer. When you move it up, boom. It keeps the characters from, our from object from going through the into objects. And you can't quite see it, but there is a little red dot that shows up on where those collisions are occurring. All right? Now, I got through that stage really fast, so we got plenty of time for the networking. Any questions over the collisions? And that includes, that's why with the server I left the camera in mouse control, because I can always, if I'm looking for someone off camera, like a client, one of the other players, I can just pull back and see where they are. Yeah, please.
Okay, so you've got your model, which defines the shape of your object. And then for collision detection, you're attaching onto that model another object node that defines the collision.
It's a collision geometry node. It's different than it's a geometry, but its use is different than basically just rendering. It doesn't render every time through the render cycle. And it's at this point probably be a good thing to mention that the render cycle means that the task manager, of course, there's a cycle that a new scene is rendered as soon as the task manager's finished all the tasks. And he says, okay, go ahead and render it. Like moving left and right. Once those tasks have been calculated, then, and the task manager has many different tasks that it's doing that are yet not seen. But the collision spheres are basically geometries because there is an actual, because you can see them rendered, right? When you give the command to show collisions, you'll see that sphere given as an opaque kind of, transparent kind of object. You need the geometries to show that. But I think your question probably implied something more.
Well, I'm just trying to figure out how the various objects are interacting. So you've got your model object, which has a collision object
Mm-hmm.
to it. And then there's a traversal object, which is going to be comparing the collision object relationships.
Mhm.
Is that correct?
Yes, yes. And basically, you still need the geometries to be able to detect it, but the collision software, the collision method, doesn't say, oh, this polygon's hitting this polygon. What it's doing is it's saying, I know this sphere is radius 1, this collision sphere is radius 2, and it only has to check the distance between the objects to make sure that that distance is either equal to or less than the sum of the two radii. So that's why the pusher is such an efficient algorithm to use for collisions. It doesn't have to go around and say, for every polygon in my object and for every polygon in the collision sphere, test to see if there is a polygon colliding with another polygon in that object. Yes.
So essentially, inside of like Panda3D library, there's an event sequence of movement, collision detection with defined objects.
Right.
In the render tree.
Right.
The whole kind of point of like having collision detection separated from the view objects is to test collision before rendering, so you don't have as much screen brush through your object.
That's right. And there are some very advanced movement algorithms in Panda that, that if, sometimes you'll find, like with some collision primitives, one primitive I have problems with all the time is a collision plane. So I have my collision sphere coming toward a plane, and I want to collide with. Sometimes that object, the sphere, goes right through the plane, because from one time cycle to the next, the collision software does not catch that collision. And so there are other kinds of manipulations you can use with the collision software that you can detect those collisions. But I think I'll leave that for another presentation. But the Panda software is very sophisticated. It can be very sophisticated. You can set it up very simply, as we've done here, or you can set it up very aggressively through extensions to the collision software. Any other questions? Okay, well, let's go. Are you ready for networking? Let's see. Okay, stage 4 in our final stages. I'm so happy to reach this stage because last year I wasn't even close. In networking, we're going to look at setting up what's called a client server. Well, now, most games are more a hybrid of the two concepts of peer-to-peer and client-server. The client-server model basically says the server is the repository of all information. You know, that the clients would just send, hey, I want to move left, and then the server would move that character left, detect the collision and say, oh, no, you're colliding, you've got to stop, and things like that. The client would say, I'm firing a missile. And then the server would say, okay, so he goes in and he starts the missile and then lets the client know where his missile is. That's a rough approximation to what client servers do. But the idea is that the server is the one who controls everything in client-server relation, in the abstract client-server paradigm. Now, peer-to-peer pushes it the other way. The clients, or the players in this case, each machine has everything about that player. And then he shares that with every other player on the network. So that, of course, you know, let's go back a minute. With the client server, you get a lot of traffic that's going from the server. The server is really taxed by the number of things it has to do to keep track of many clients. Here with the peer-to-peer, the traffic on the network increases tremendously, because not only are you communicating with, you're no longer communicating with just a server in this instance, but you're communicating with n other players on the network. In this case, 4, or 3, I should say. So let's look at what the server has to do. We're going to do a hybrid of this. The server has to listen for information from the clients. First of all, a client or a player requests to get access to the game. Excuse me. Then, if the access is granted, unless there is some sort of problem with the network in which there's a lag time or something, but then the server has to inform all the clients about that single player being added to the game. And we also have to inform, the server has to keep track and let everyone else know when that player moves within their game, which means that player is moving within the shared game. Now, all these games are operating on these different machines, and there's not one environment, but there's n different environments going on at the same time. And you just hope that the network is handling it so that they all are occurring without error. You know, that the player that moves from here to here is not really over here, and so forth, and things like that. So the client responsibility is to send the server information, you know, requesting access to the game, motion updates, and when they want to quit. So the server script. So this is the one stage where we're going to divide the scripts into 2 different scripts. We're going to do one for the server and one for the client because they have different responsibilities. The configuration file that I should point out is a separate file that is in the folder, and we'll look at that when we're done with the talk here. It has 3 simple statements in it. We have a variable called myID equals, and of course, some kind of a name. Like for me, it's Big Kahuna. The server number is that dotted decimal number that identifies the routing number or the network number for that machine, the server machine, and the port number as well. The port is, I always use the analogy, the port number is kind of like an apartment number within an apartment complex. Each port number has a responsibility. Some of the lower port numbers are responsible for like HTML access and other kind of features on the network that are reserved for those lower port numbers. And I've heard the value that you can, a good value to use is anything really above 5,000. Okay. Now, ipconfig is a command that you can use in your console to find out information about your machine and its connection to the internet. The line that is of most importance to us is that one that says IPv4 address. That's your internet address on that machine. And it has 4 fields, and usually the individual identifying information is that last decimal, the 105 in this case. Now, the client scripts use a separate configuration file because we want to name the client something different than Big Kahuna. Because we're going to set up, when we set up our players, we're going to be creating data that is unique to that machine and that player, and that is by ID. Have you ever tried to join a game? And of course, the thing they do is you say, gee, I'd like to play this game, and they say, okay, send us a name. Send us your player name. And they say, and you send them something. Say that's no good. You got to choose something else. That's because every game needs to identify the players uniquely, and that is typically done by the ID name, the player name. And now, the server value that you would fill in for that config file is the server ID, the server field, IP address. And so whatever that server IP address would be, the server has to send that information to you, and you would fill that in. Or more likely, the people that are selling the game would send you some sort of encrypted configuration file that would automatically read that information. And certainly a lot of games these days have many servers so that you're rotated from server to server without you even knowing it. And the port number, of course. Then the port number is also something set up by the people developing the game. Now, the network section of the code, those tags that you saw earlier, these we're going to be sending messages between client and server and back again. We're going to have a two-way communication going with the client and the server. And we are going to, the first value on those messages is going to be what type of message it is. One, we have a default none type message, which has the ID of 0. Then the authorization equals 1 is a message that is passed to the server that says, I want into the game. The POS command is a message that is sending position information to the server. The quit is the two kinds of quit and two kinds of position, I should say, are basically between one, when the client is saying I'm quitting or I'm changing position, and then the cpose and the cquit is the server sending a different message telling everyone, hey, this guy is changing position or he's quitting. So the one is meant to be broadcast by the server. The other is a message that is identified by sending from client to server. Now, I'm going to get into a little Python ease here. We're going to talk about dictionaries. And this is basically the data type that we're going to be using to maintain the information in our game. The client's dictionary sets up the server detects the connection from the person asking for entry into the game. And dictionaries are created by key-value pairs. For a key, You can look up your key, and then you get a value that is associated with that key. So with the connection, we have a player ID. The player list is a dictionary that basically has the player ID as the key, and then the value is a data type that shows the 6 pertinent values for that player. XYZ for position, and HPR for orientation. Those are the most important things for us in this game. We need a dictionary that by player ID is the key that shows what kind of model they're using and what to render. The dictionary called Cole spheres. Now these are not reserved names by Panda. These are names that I invented that meant something to me, so I could work with these dictionaries. But Cole spheres, again, the key is player ID. The value is the collision sphere. What is the collision sphere that is identified with this player? Very much like what we set up with the fighter and the parent, and the collision nodes as well. We're going to be attaching collision nodes to collision collision spheres to collision nodes. I kind of listed those in opposite order. Now this code is placed in the constructor because the constructor, again, is going to define the game. And the last command in the constructor is a call to what I created a function called a init network. So once we've gone through that constructor, we should have the environment for our game created. And we can now call different functions, get out of the constructor, and just let the game go from function to function based on the event driven for movement. The movement causes messages to be passed, and then those messages being passed creates an environment where the server informs every other player. Now the connection manager queues up all the connection messages. And we'll see the code to that in just a second. Likewise, the connection listener is something that's only on the server, and it's basically listening. It's a process by which the server is always listening for someone to ask for access to the game. The reader queues up all the datagrams that are being sent to it, and that the reader is common to both the client and the server because they're all looking for messages to read. And the connection writer basically, again, are also connected to the sockets that are connected between the connection information, and basically through the port number and the IP address. And then after a init network, we start the server, and those are basically functions that I've written that contain information that start specifically the server and the client, and those are in each of the separate codes. Starting the server, it opens up a TCP connection. I use a TCP connection because it's not probably the best way because it always asks for acknowledgement that a message has been received, and that can slow down a game. But Panda does have a UDP connection server that you can, a basic UDP just says, I don't care. I'm just sending this message, and I don't really care if they got it or not. It's just gone, and I don't have to worry about it anymore. And so at one of these days, I'm going to implement the UDP and see just if we get some improvements in communication. So the listener adds a connection to the TCP socket with the add connection, and the server adds himself to the player list. And you can see what it looks like there, what the dictionary call looks like. My ID is the one that's the key, and the associated value with that key in that dictionary player list is the 6 values XYZ HPR. So we start at X is 0, Y is 0, Z slightly elevated in the Z axis, and the HPR is 0, 0, 0. So we no realignment of the orientation. And below the dot, below that is again stating that a Python dictionary, the key is the ID, in my case, the big kahuna for the server, and the value is, the value are those 6 values, floating point values, that determine the placement and orientation. Now the network code, for starting the server, we add tasks to the task manager. And these are in addition to all the movement tasks of left, right, up, down arrows. The task manager runs every game cycle. It executes registered functions like a task that's set up for listening, a task that's set up for read, and a task that's set up for a function called update. Okay. So it's instructed to do these tasks every clock cycle, as the clients are as well. The clients don't have a listen task, but they do have a read and an update task. The write task is kind of done as needed. You don't need a task for writing. You just create a message and you send it out. So the server is listening for players that want entry into the game. And in the network section code, starting the client, again, we open a TCP connection with the IP address and port number. We create a read connection, again, that is going to be included in the task manager. And we create a spawn point for the player. In this case, what I did was I put in the random function, a random X and Y, so that the player is positioned randomly when he comes into the game. And we're playing with Z equals 0 all the time. It's just going to be a 2D game, just on the one plane. Now, datagrams are an interesting part of this whole communication. The Pi datagrams, and I think that, that many other games use the same system of creating those communication datagrams. They're internet packets. And everything that is contained in the datagram, how the datagram is stored and sent, is all within the Panda libraries. We're going to take a very top-down top approach to creating our datagrams. But they are internet packets that can be sent over the internet. Here's an example. They're going to be built on the set get methods, and they're based on strings, integers, and floats. That's the 3 primary data types that we're going to be sending in datagrams. And so you see a datagram there. I'm not sure if you can see all the details, but that top line in that box is MSG authorization. This is going to be an authorization message that the client is going to send the server. We're going to add that integer. The message AUTH, remember, is the digit 1, is the integer 1. We add the string, which identifies the player ID. And on each machine, the player ID is generated as self.myID. And we add the 6 floating point numbers that are labeled add float 64. And we have XYZ HPR filled with some floating point value as a variable. And that creates the datagram. Now, the client sends a request to join the game,
and only the clients send the authorization message. They're the only ones that really want to join the game. The server is already in play. And the server adds players to the player list, and the server is the only one to receive a authorization request. And once the server has added a player to the player list, the purpose of the server would be to blast another message, not an authorization message, but one of those POS messages that says, hey, this guy's added, you got to add them to your table, your dictionary. He's now a player in the game. So every time you push, the client pushes an arrow key to move, they should send a message to the server saying, I just did that. Now, to give you an idea of what's going on, I think the task manager or the clock cycle runs about 5,000 clock cycles per second in a typical game. At least I've seen it as high as that in some, when I've put some software on my games and measured how many clock cycles were running. So it's happening quickly. So hopefully you get correct updating with 5,000 tasks being done a second. Let's see. So let's see what, I think this section, event-driven, you push the key, you update your model. So here's how everything works. A client pushes a key. He pushes the model in his machine to the correct location. Sends a message to the server saying, I'm here now, XYZ HPR. Okay. Now we're not dealing with HPR right now with this game design. We're not really changing the orientation. Maybe sometime in the future I can come up with the same design, make it look like the character is pointed so we can actually fire things at other people, make them explode. But that's for some other Pi Ohio. So you push the key, you update your model, you inform the server informs all the other players. The server puts that client in the correct place, and so do the other clients. So that all the models that are running on all the different machines hopefully have the same message at about the same time. At least within the status of the game, so that everything else that's happening in the game is happening in a coordinated fashion. And so here, what happens is, I'm showing that how on the left-hand side, we're adding information to our authorization key. Actually, that top line should be CPOS rather than anything else, but that's a typo. So this is going to be a position datagram. We add my ID, so we're basically telling the server what my position is. With XYZ, HPR will always be 0 in our game. And then what happens is on the server side, as well as on all the other client sides, they have the equivalent method of stripping that out from the datagram. First of all, they get the string, or they first of all get what kind of message it is from the top bar. Then it gets the player ID, then it gets the XYZ HPR and changes that player's position information in the dictionary. That is the player dictionary. Okay. And then the renderer, of course, is supposed to be directed toward that information and renders the client in a new position. So when I should add, the instancing of a datagram is that top line on the left. DTA equals pi datagram basically instances a datagram with that command. So DTA now has all the methods that the PyDatagram has included as a class. And we call on the add uint16, and we add the integer that is equivalent to that MSG cquit. I forget what it was, whether 4 or 5 or something, but some integer. And then we also, to that message, we add the string that is my ID. Now notice the difference between the quit message and the position information. It's quite simple. All we tell the server is saying, I'm quitting. And then the server says, okay, I'm going to shut down all the information that was pertained to you, and we're going to remove you from the render scene, and I'm going to tell the other players to do the same. And that's with the getString method on the other side. So basically, we're going to be looking at the scripts. We've got a server script and a client script. Both scripts are complete. Start the server. First of all, you start the server. And when we get a connection, the clients should be a blue sphere outside the circle, and all other players appear as spheres on their host machine, red spheres. So basically, we can design it another way, but when the host machine for a particular player uses that self.fighter variable as its own hero, its own player, and it's colored red, okay? And that happens on all the other machines. We distribute it so that all the other machines, that everyone who runs that code will always be a red sphere. And I think that I'm mistaken there, but I think that all the other players that come into the game appear as cubes, blue cubes, to show that they are even the server is a blue cube on someone else's machine. But those are things that you can control when you're designing your Python environment and your Panda environment. You can direct it toward, like, clients will always have a certain geometry and a certain color. The server will always be the red sphere, whether it be on my machine or a client machine. But those are all programming, details. Now, the thing we must make sure is that we get the correct IP address for the server and the different usernames. Must make sure that, because if we have the same username as keys in 2 different locations in those dictionaries, there'd be ambiguity. We wouldn't know. We say, hey, look up the position of Big Kahuna. So it would be completely random as to what Big Kahuna you're retrieving for a position. So you have to make sure that the usernames are different. Okay, so let's take a look at see if we can see how this stuff is working. And I'm going to go to the final code. Let's open up the server. Okay. Now again, the top part is for calling in libraries that we're going to need in our calculation. Notice in the middle, right here, it says import the PyDatagram. Okay, so we need that. Let's see if I can. Unfortunately, I can't scroll this window larger. Let me try real quick to just see if we can go down, step down one. There's 22, let's go to 20. Bold. So we can see at least more code anyway, 18. Can you still read that? Okay, good. So all these libraries have different components that we are going to use in our developing our game. Notice here, down below, our message coding. We have different integers that mean different types of pi datagrams that are going to be created. The timeout is basically a feature that after a particular machine tries to access and is returned, that the server no longer tries to connect. Let's see. Where are we? So basically, let's go down to the end of, we've been through this, we've created our wall. Now with the, here I've set the camera to a certain position and orientation. And we've got our key bindings. Here we have the collisions. And here we're done with everything setting up the game we're going to call a init network. Okay. Yes? Oh, they're 5 minutes? Got it. All right. Let me go through real quick. Not enough time to show you the connectivity, so I'm sorry about that. But the code is there. If I were to bring up the server side, you wouldn't see anything particular. But let's do something. What you need to do is to, my cursor, here are our two networks. If I look at, I'm going to open this in Notepad. Here is the network for the server. Notice the game's Big Kahuna. And I got this IP address. I think I'm still connected. You run IP config, and you get all the, oh, okay, I'm not connected. Let's see. Well, if I were to connect to the wireless in here, you would see a value in there called IPv4 connection. And it would show you a dotted decimal, very much like, where is it? I hate being rushed. That's not it. Well, very much like this one. And actually, for those of you that that might even like to try and do home gaming, you can get a inexpensive router like this one, and you can connect through Ethernet through some ports in the back, and this router auto-creates IP addresses. So every machine that's connected to this router will get a separate IP address. And then you can set up one machine as the server, run the server code, and then put that IP address of the server in the other config files, which is, so this is the server, the one the server reads, and you got to make sure that the port numbers are the same and the IP addresses are the same. Names have to be different. So let me open up the, here's the client. Okay, now notice the only thing that's different, well, should be different, is the name. So this client's named Rampage, you know. Same server, the server equals the IP address, which is the same as the address you would get from the server, and so forth and so on. Okay. So if you want to try this at home, you could take this code, and I was running it the other day, so I keep my fingers crossed if you take it home and you try and run the done code, because in that final code folder are the finished code for the client and the server. Okay. I guess I am done. Yes?
Does the Panda3D library require like a direct draw or OpenGL?
It works, I believe, with both DirectX and OpenGL.
Does it work on like
No. I do not know. Let me put it that way. I have not experimented with that. I mean, I use Unity as well as a game engine. Of course, Unity has the licensing that you can generate iOS, Android code and port them, but Panda I'm not aware of. And I believe that if they were going to stay competitive with every other game engine, they probably should have developed that. But I'm not aware of it. I'd have to do some research. Okay. If you want to know more about Panda, go to panda.org. There's a manual page there. It's very insufficient. I know my students hate it because they really have to dig to find out what they need, because it's not like a thorough, complete manual that someone like Visual Studio would put out or something like that. The people that charge money, so they should make something very professional. I'm trying to think if there's anything more I should tell you, but I'm just going to say good luck. You have my email. I don't know, do you want me to put up that slide of the Dropbox so you can download it? Or if you do, I'll do that at the end and keep it up for as long as I can. And thank you, and wish you a lot of luck. Good gaming.